All right. Hello, everyone. So, welcome back. If you are watching these kind of in the order that I put them out and you haven't worked ahead at all, this should be the first lecture directly after our midterm exam. So, hopefully, the midterm went well for everyone. Everyone feels decent, and we're ready to start off the second half of the course. So, this lecture is going to be a little bit weird. We're going to be doing sections 4.1 and 4.4 just because they're both kind of shorter. And I'm not going to be covering everything from 4.4. So, 4.1 is going to be applied calculus. We're not really going to be doing anything new in this section. It's just going to be applying what we know already. So this is going to be using the stuff that we should be really solid on considering we just took the midterm. So this is chapter 4, applications of derivatives. And we'll start off by just seeing a quick application. So a very common example that you may see is something like a rocket being launched, and we want to see some sort of rate. We're looking at rates. So we know that slope is derivative, and slope derivative also kind of discusses the rate of something happening. So you take a derivative, you get a rate. That's the same thing as saying like velocity, right? So this is an example of saying at what rate should the angle of the video camera essentially change to be able to have the rocket in its sight the entire time. And these are some good examples of what it's like to be trying to apply calculus to the real world. So as opposed to maybe pre-calc where the applications were a little bit more scarce, in calculus, especially in this chapter, we see a lot more real world applications and things that you could actually see and could actually have to use depending on your career. All right, so let's get into it. So this will be section 4.1. Again, today we're doing 4.1 and 4.4. So this is 4.1 and it's called related rates. All right, so here is the problem solving strategy for related rates. So essentially what we want to do first is we want to assign symbols or letters to all variables in the problem. So if I see something, um, that represents volume, I'll probably call it V. I'll assign whatever makes sense to me. And something that's also very important is we want to draw pictures. It kind of helps us understand what's going on. All right. The next thing we want to do is state in terms of the variables we just kind of found, the information that's given, and we want to figure out what it is we're trying to find. Typically, we're going to want to find a rate. Sometimes we're going to be given the rates and asked to find something else, but rates are always going to be included because, again, this is calculus and that's just kind of what we're dealing with. So we're going to try to figure out what exactly it is that we are looking for. We should only have one variable because this isn't going to be like a system of linear equations where we're looking to solve for multiple variables. We're just going to be looking for a single variable. So if at any point you're missing two variables, you'll need to find a way to solve for one of them. And we will see an example where that's the case. All right. Step 3 is going to be find an equation relating the variables introduced in step 1. That just means find a formula. Typically, these types of related rate questions are going to be of shapes that we're familiar with. We'll see spheres, triangles, cones, rectangles, rectangular prisms. You can see any shape you're familiar with. And this should be a little throwback to, I'll say, high school geometry, where we should just be familiar with all of the volume and area and surface area formulas from those specific topics. So if I give you a sphere, which will be our first example, we should know that the volume is 4/3 pi r cubed. We should know the area is pi r squared, depending on what it is that we're looking for. All right, after we find an equation, we're going to use the chain rule to differentiate both sides with respect to the independent variable. All right, so we want to take the derivative with respect to the variable that we are looking to solve for. All right, this new equation will relate the derivatives. So every single derivative, you might recall implicit differentiation when we had y and x. We took the derivative of y, we wrote dy dx. Well, now we're not doing things with dx in mind. Related rates is a rate, which means that we are looking in terms of time. And so we are going to be doing the derivative with respect to time. So everything we take the derivative of, we do have to then multiply it by the derivative of whatever it is with respect to time. So if we take the derivative of v, then we have to say the derivative of v is dv dt. or the derivative of r, if we're talking about a radius, as dr dt. So everything will be with respect to t now because we're talking about something with respect to time. So that's like the major change in this topic. And then 5, after we take the derivative, we want to substitute all of the values that we have into the equation and solve for what it is that we're looking for. A very, very important note is that we don't want to substitute things in too soon. So you might be inclined to create like a volume formula and say, oh, I know the radius, let me plug it in. The radius is not going to be a constant. So if it was constant, obviously there would be no rate. If you're just given like a soccer ball, there's no rate. But if you're, say, inflating a soccer ball, it is inflating at a specific rate. And so the radius is changing. Even if you're looking for like an instantaneous snapshot, you're not going to be looking at a radius just at a specific point. You're going to also have to consider the rate at which the radius is changing. And so make sure you're not plugging anything in until after you take all of your derivatives. All right, unless it specifies this thing stays constant the entire time, we're not going to plug anything in. All right, and if you ever see the word rate, just remember that is your derivative function. So if you're told here's some value, that's probably just going to be a regular old value. If you're told it's happening at a rate, or even if they don't say the word rate and they say it's changing at like 10 feet per second, that is just a rate. So make sure that that is going to be a derivative when you plug it in. All right. So let's go ahead and take a look at a few examples. So here's the first one. This is talking about inflating a balloon. A spherical balloon is being filled with air at a constant rate of 2 centimeters cubed per second. Now, I know it says constant, but that doesn't mean we plug it in right away because it's a rate. So obviously we don't have any derivatives right off the bat. How fast is the radius increasing when the radius is 3 centimeters? So again, this isn't saying that we have a constant radius of 3 centimeters. This is saying if we just kind of take a snapshot right when it's 3 centimeters, what is happening to the radius? How fast is it changing? So the first thing we have to consider is what equation are we going to want to use? And I know it's written off to the side, but this is just something that we have to think about. So if it's a spherical balloon and we're inflating it, then obviously we're doing something to the volume of that balloon. And so we have to remember if it's a sphere, the volume of a sphere is 4/3 pi r cubed. All right, so once we remember that formula, we can write that down. And next we can go ahead and kind of identify what we're given. So we're given that we are filling it with air at a constant rate of 2 centimeters cubed per second. So if we're being filled with air, that means the volume is changing at 2 cubic centimeters a second. So that means that the rate of the volume, which is dV dt, is 2. If it said it was deflating, we would say -2. But since it's inflating, we say +2. So how fast is the radius increasing? So since we're looking at a rate here, that's dr, I'll call the radius r, dt, and we're looking for that value when the radius is 3. So we'll say r equals 3. So the first step is to just kind of name all of our variables and then write them down off to the side. Now that we see all of those things, we know that we need a derivative, and we obviously don't have that here. So we're going to take the derivative using the chain rule. So first we'll take the derivative of v. The derivative of v is just dv dt equals 4/3 and pi are both coefficients to the r cubed. So that's 4/3 pi. And then we take the derivative of r cubed using chain rule. So bring the 3 down. So this is times 3 r squared. Let me kind of box this off. But then chain rule says we multiply dr by dr dt. All right, let's simplify this a tiny little bit. So we have dv dt equals, so 4/3 times 3 is just 4 pi r squared dr dt. So I just multiplied the 4/3 and the 3. I never multiply in your pi. We always want things in exact form, and pi is exact. All right, now once we have our derivative, we can just go ahead and plug in the values, and we should only wind up with a single variable that we're looking for. So we have that dv dt is 2, so 2 equals 4 pi. We have r, which is 3. We know that's squared, and then dr dt is what we're looking for. So all we have to do is divide by 4 pi times 3 squared, which will be 9, and then we can have our answer. So dr dt equals 2 over 4 pi times 3 squared. And if you were to simplify this, you would get that this is 1 over 18 pi. And our units on that will be just regular old centimeters per second. All right, and this is the rate at which the radius is increasing at specifically 3 centimeters. So it will be different if you were to plug in a different value here. All right, let's take a look at another example. We only have 3 examples for this section. So an airplane is flying overhead at a constant elevation of 4,000 feet. So I give you the drawings here. You would be expected to be able to produce the drawings on your own, given like an assignment or an assessment. An airplane is flying at a constant elevation of 4,000 feet. So this isn't saying that the rate is 4,000 feet. This is saying the elevation is 4,000 feet. Since it's constant, we can actually plug this value in from the beginning. But this is the only case that we'll be able to plug something in from the start. We don't even necessarily need to. It won't change it if we don't. A man is viewing the plane from a position 3,000 feet from the base of the radio tower. All right. So we have a man, and he's 3,000 feet from the base of a radio tower. So we know this value here will be 3,000 feet since here's the radio tower. We know that the airplane is flying at 4,000 feet, which is above the ground. So if the ground is the X value here, then up here is 4,000, which is already written in here. The airplane is flying horizontally away from the man, so this direction. If the plane is flying at a rate of 600 feet per second, so typically the way that I'll represent that in a drawing is I will put an arrow and then I'll write the units next to it. So I'll say 600 feet per second because arrows represent rates. At what rate is the distance between the man and the plane increasing when the plane passes over the radio tower? So now we're looking for the rate of the distance between the man and the plane. So the distance between the man and the plane will be from here to here, which is the hypotenuse of this triangle. All right, so we're looking for, if they call this S, you can call this whatever you want. We're looking for this here, which we'll say is ds dt, and we don't know what this is. So the first thing is I'm going to go ahead and write down kind of everything that we know off to the side. So I know that if we call this X down here, the base of our triangle, X is 3,000. I can call this H. H is 4,000. Well, S here is a hypotenuse. If I know the base of the triangle is 3,000 and the height of the triangle is 4,000, I can in fact find the hypotenuse of the triangle. I can find that using the Pythagorean theorem. So I can say a squared plus b squared equals c squared. So 3,000 squared plus 4,000 squared equals c squared. And if you do that calculation, you get that, well, I'll just jump to regular old c equals 5,000. So here, this is s is 5,000. Now we can kind of look at the rates. So we have no rate happening right here. We know that this is flying at a constant elevation. And so the rate here is going to be 0 if you want to write a rate in, but we don't have to consider that at all. That's why we can put this in as a constant. This, however, is changing since the plane is flying away from the man. So I'm going to say this is dx over, dt. And we have ds dt. So we have dx dt and ds dt. And we know we're solving for this one, which means that we have to have this one. So let's go back into the question. It says the airplane is flying away from the man at 600 feet per second. So if we're going this way, that's the same thing as saying right here, we're going away from the man. So that is 600 feet per second. All right, so we have all this information now. Let's go ahead and figure out a formula that we'll need to take the derivative of. Since we have a triangle, the most logical formula that we're going to have to use is the one that we've already used. So we're going to say a squared plus b squared equals c squared. But instead of just solving something, we're actually going to take the derivative of this thing. Now, there's kind of two different ways that we can do it. I'll show you why it doesn't matter if you plug in the 4,000. So like I said, this is not changing at all. So this is, I guess, changing at 0 feet per second, if you want to think about it like that. If it's not changing, then it's changing at 0. So to derive this, take the derivative of a squared, that's 2a dA dt. The derivative of b squared is 2b dB dt, and the derivative of c squared is 2c dc dt. And if I go ahead and actually plug in the variables that we've called it, first of all, I can divide everything by 2 since they all have 2 in common. So our a is like our x here. So this could be the same thing as saying x dx dt plus the b is like the height here. So we call that h dh dt. So this will be dh dt. And then the c is the hypotenuse, which we called s, which I don't love using as a variable because my s's look like 5s, but that's okay. We'll know that it's an s here. ds dt. So all I did was change my variables here. All right, once I've taken my derivative, I can go ahead and plug my values in. So x we know is 3,000. dx dt we know is 600. Plus h we know is 4,000. But dh dt is 0. And then s is, we solved for 5,000, but then we don't know ds dt. That's what we're trying to solve for. So ds dt. So right here is exactly why if you have a constant that is not a rate, we don't necessarily have to take the derivative of that term. We can just plug it in because the derivative of a constant is just 0. And so this whole thing just goes away. So what we actually get is 3,000 times 600 equals 5,000 ds dt. And if you solve that, what you get is ds dt equals, let's see, it is 360, and the units will be feet per second. All right, we got one more. This one is definitely a bit harder because now we have the situation that I said where we actually have two variables, but we're not looking to solve a system of equations. We need it in terms of a single variable. So we are given that water is draining from the bottom of a cone-shaped funnel at the rate of 0.3 feet per second. So if we know that we're draining at a rate of this thing, that means the volume is changing at this specific rate. So that means that dV dt is going to be this rate right here. So what we'll get, let's see here. Yeah, sorry, I was just checking my notes over here. So what we get is that this is 0.3, 0.03. And I'm actually not going to include a unit because we have it in the question, and that's kind of redundant. So I'll just say 0.03. All right, the height of the funnel is 2 feet, and the radius is 1 foot. So we have the height is 2 feet, radius is 1 foot. Now I'm not going to write that in yet, and I'll show you why. At what rate is the height of the water in the funnel changing? So this is what we're looking for. The rate, the height is changing. So we're looking for dH dt. So I'll put equals question mark when the height of the water is a half of a foot. So this is why I didn't write it down, because it's saying when the height is 1/2. So h equals a half of a foot. And again, you don't have to write the units here. So we have a slight issue here because in this case, we're not given anything about the radius, but we are given something about the radius here. So we need to kind of take that into consideration. We have information about a radius, but we don't know the radius when the height of the water is a half of a foot. We know the radius when the height is 2 feet, right? It's 1. But that's not what we're looking for. So what we actually have to do is recognize if this is a cone, the volume, since we're looking at volume, is 1/3 pi r squared h. So we need to solve for an R. We can't have two variables because if you were to take the derivative of this, what you have to do is use the product rule, but then you get you get dr dt and dh dt, so you're looking at the radius at which the rate is changing. Yeah, and we don't have anything about the radius changing. So that's a problem. But we have a proportion. They've given us something that we can create a proportion out of. And in fact, if you look here, I'm going to sketch it in. Here's the smaller area. You notice this is a right triangle. Here's the bigger area. And you notice this is a right triangle. And so what they've actually given us is similar triangles. And again, this is a major throwback to high school geometry, is playing around with similar triangles. So now that we know that we have similar triangles, we can actually go ahead and use the properties of similar triangles to set up a proportion. So what do we know? Well, if we are looking at the proportion of the radius over the height, I just chose this at random. You could do height over radius if you wanted to. Well, I know that what they give us for the big triangle here is the radius is 1 and the height is 2. All right, here's 1 foot, here's 2 feet. Well, what does that tell us about the height? Because we know we need everything just in terms of h because we need dh dt. We have no information about r. Well, that tells us that we can solve r for h. Well, that tells us if we multiply both sides by h, that r is h over 2. That helps us because if we plug in for r, now we have everything just in terms of h. So that's exactly what we're going to do. So anytime you have a variable where you don't have any information about the rate, and in fact, it would just kind of be more messy to keep it in, we're going to solve to kind of get rid of that variable to make it in terms of the other variable that we have. All right. So here we have r equals h over 2. We used the information that they gave us, the 1 and the 2. They didn't give that to us just kind of to throw us off. They're always going to give us information that we need. So that's where we're going to be using this information. And then this 1/2 is going to come into play when we actually plug things in later on. So now that we know this, we can actually go ahead and adjust our formula. So now our volume formula is 1/3 pi, but not r. R is going to actually be h over 2. So h over 2, but that's squared, times h. And then I'm going to simplify that before we have to take our derivative. So this is going to be, let's see. So the 2 squared will give us a denominator of 4 times 3 will be 12. So this is 1 over 12 pi. Let's kind of box this off. H squared times h is h cubed. All right, because this is a heck of a lot easier to take the derivative of than this guy right here, which you'd have to use product rule if you didn't simplify. Okay, now we can go ahead and actually take the derivative. So the derivative of v is again dv dt equals 1 over 12 pi is the coefficient on the h. So we can just leave 1 over 12 pi and take the derivative of the h cubed. So bring the 3 down. So that's 3 h squared times dh dt. If I were to simplify this, 3 times 1 over 12 is 1 over 4 pi h squared dh dt. And this is still dv dt. And now we can kind of look and ask ourselves, well, do we have enough information to plug in? Is everything looking good? Well, we have dv dt, we have h, we're looking for dh dt. So it looks pretty good. All right, so dv dt is 0 0.03 equals 1 over 4 pi, h is 1/2, given that we are looking at it at the snapshot of a half of a foot, squared times dh dt. So all we have to do is do 0 0.03 divided by 1/4 pi times a half squared, which tells us that dh dt equals, and I'll just kind of give you the answer. It's a funky looking answer. It's negative 0.48 over pi feet per second. So at what rate is the height of the water changing? This is saying that it is decreasing at this rate when we're at half of a foot. All right. So this is the last example from this section. I'm going to go ahead and pause this video really quickly and pull up the next section, and then we can get a jump on that one. All right. So here we are now with the mean value theorem. So we can go ahead and start talking about what is the mean value theorem. All right, so here is a little visual representation of what exactly the mean value theorem is. So here is just some random graph, and we have two different points, and we're looking at the slopes of the tangent lines at that point. And then we have a starting point and an ending point, and then the slope of the secant line, which is just the line that connects those 2 points. So essentially the mean value theorem, it says it down here, is we're looking for a tangent line that has the same slope as the secant line between the endpoints. So let's go ahead and actually get a formal definition of that. So the mean value theorem says, let f be continuous over the closed interval a to b and differentiable over the open interval a to b. So the reason why we want it open here is because this is going to be a closed interval, which means that the limit, for example, from a, from the right exists, but the left does not exist. And so we can't differentiate at a or b. So it has to be open when we actually look at the area where it is differentiable. Then there exists at least point C in A to B. All right, so this notation, again, this reads C in A to B. This is just kind of notation, shorthand math, because we don't like to write things, such that f prime of C equals f of B minus f of A over B minus A. You'll recognize this as just the slope of a line given an endpoint or given 2 endpoints. So this is saying that there's some f prime of C that the slope of the tangent line is equal to the slope of the secant line, which is exactly what we saw. If you want to see the proof of that, this is a link. All right. So there aren't too many examples that we're going to do with this, honestly. The most important part of the mean value theorem, in my opinion, again, this is a pretty short section, is going to be the corollaries that I'm going to give you after we do this example. But we are going to do an example just for you to see exactly what it is that the applications can have. So if a rock is dropped from a height of 100 feet and its position t seconds after it's dropped until it hits the ground is given by s of t, again, s of t is a position function, equals negative 16 t squared plus 100. We want to find these things. So A, we want to determine how long it takes before the rock hits the ground. So that's not too hard. This doesn't even use calculus. We know when something hits the ground, that means that it is a 0 of the function. So for A, what we need is negative 16 t squared plus 100 to be equal to 0, and we need to solve that. So if you were to solve that, I'm not going to do all of the algebra for that because I trust, especially at this point in the course, that you guys can move the 100, divide, square root, do all of that stuff. What we get is that t is equal to 5 over 2. Now, since it is squared, you will get a plus or a minus when you take the square root, but it's important to note that, especially in the second half of the course, especially looking at applied situations, when you're dealing with time, there's no negative time. And so if you get a negative value, you're going to reject that because there's no such thing as negative time. Okay, so time is 5/2. So, and this isn't asked, but the interval that we're going to be looking at is from 0 to 5 over 2. Because obviously we're going to start at 0 seconds because there's no such thing as negative 1 seconds, but we're going to end at 5/2 seconds because that's when the rock hits the ground and you can't go below ground because that's weird. Okay, B, find the average velocity of the rock for when the rock is released and hits the ground. All right. So average velocity, we have to recall that formula. I believe we did that before the last exam. So the average velocity is actually more or less just the formula that we were looking at for the mean value theorem. Actually, it is the formula for the mean value theorem. So that's going to be S of B minus S of A over B minus A, where A and B are the endpoints that we've created. So that's why I wrote it in this notation here. So that's saying S of 5 over 2 minus s of 0 over b, which is 5 over 2 minus 0 is just 5 over 2. So at 5 over 2, we know we just solved for the zeros of that. So we know that's when it hits the ground. So that has to be 0 minus at 0, we could plug in 0. Well, 0 here just goes to 0 plus 100. So we just get 100 over 5 over 2. And when you actually compute that, you get negative 40 feet per second. So that's the average velocity. Now, for C, we want to find the time guaranteed by the mean value theorem when the instantaneous velocity is the average velocity. So that was just the statement in the mean value theorem. So let's go ahead and figure that one out. So the first thing that we have to remember is that the regular old velocity function, which is where we'll get the instantaneous velocity from, is the derivative of the position function. So s prime of t is v of t, which is, if you take the derivative of this function, negative 32t, and then the 100 will go away. So if we're looking to find when the instantaneous velocity is the average velocity, we have to consider the notation that we were given in the slide before. So that was saying f prime of c is equal to this thing here. So we will go ahead and consider the variable to be c. So s prime of c, which is v of c, equals negative 32c. So I just kind of plugged in c here, just because it was the statement in the mean value theorem that we had from our actual definition. If we know that we want the instantaneous velocity to be equal to the average velocity, then I know this being the instantaneous velocity, negative 32c, needs to be equal to the average velocity, which we said was negative 40, which tells us we can solve for c very easily, that this is 5 over 4, and this will just be in seconds. So this guarantees that the instantaneous velocity will be the average velocity at 5 over 4 seconds. So this is just kind of the type of application that you can see when it comes to a mean value theorem question. All right, and this is the diagram of what it is that I just kind of went over. So we see that we start here, we end here. This is what we solve for. We see that at 5/4 of a second, this is the tangent line. This is the secant line. Those two lines are parallel. They have the same slope, which means they have the same derivative. So that's the guarantee of the mean value theorem. It's important to kind of understand the idea of the mean value theorem. Its applications aren't the most important thing out of this course, I'm going to say. Again, the most important thing that we're going to do right now is going to be the corollaries that will come from the mean value theorem. So fun fact, corollary, I don't remember where the word originates from, but corollary kind of means a gift from a theorem. So this is coming from the mean value theorem, and these are all like gifts from the mean value theorem that we can assume are going to be true and very easily prove to be true because we know that the theorem itself is true. So these are very important. So these are the three corollaries. So number one, it says if f is differentiable, then if the derivative is 0 for all x in some interval, so it's constant, it's 0 for the entire thing, then the function is constant in that interval. So if the derivative is 0 everywhere, then it has to be constant everywhere, is what it's saying. We know that the derivative is 0 implies that we usually have a maximum or a minimum in a function, and that's only because that the derivative is non-zero other places. But if it is 0 everywhere, that means it's just constant everywhere. All right, the second corollary says if f and g are differentiable over some interval, and we have that the derivatives are equal for all x in whatever interval that you're given, then f is equal to g plus some constant c. All right, and we can prove this very easily. Consider just taking the derivative. So the derivative of f is f prime, the derivative of g is g prime, the derivative of c is 0 because c is a constant. So that immediately proves this theorem right here, or this corollary. All right, corollary 3 is a very important corollary. So if f is continuous over the closed bounded interval a to b and differentiable over the open interval a to b, then if the first derivative is positive. So if it's greater than 0 for all x in your interval, any interval at all, in fact, it doesn't have to be the entire interval, it could be anything, then f is an increasing function. So if your derivative is positive, then your function is increasing, your original function. And this is something that I believe that I mentioned when we were originally talking about derivatives being slope. We had kind of a graph, and I said, look, the slope is positive, and we can note that the derivative will be a positive value. The second part is if the first derivative is less than 0, then it's a decreasing function. So this is a very important corollary. So this is it for this section, or these two sections. We will jump back to 4.2 for the next video. This was all we had out of the mean value theorem. If you look in the textbook, there is something else called the Rolle's theorem, which is very similar to the mean value theorem, just has a few things changed. We don't cover that in this class. But these are really the important things. Make sure we know, and we're definitely going to talk a whole lot more about this. So don't think that this is the last time you're seeing that. All right. So if you have any questions, as always, let me know, and I will see you for the next video.